Awesome, we've done really well. We're already up to sequences. So if your brain needs a bit of a break, feel free to pause the video. But if you're happy to keep coming along for the ride, then let's get started on sequences. So sequences, we have our two types. Does anybody remember what our two types of sequences are? Hopefully it's thought of maybe something along the lines of arithmetic and geometric sequences. So sequences are a series of numbers that follow a pattern, unless it's a random sequence, which is kind of given away in the name, that it's a bit of a random sequence. But when we're talking about sequences, we're talking about a series of numbers that follow a pattern. So a sequence can be as simple as 2, 4, 6, 8, 10, 12. So we're following a pattern. All I'm doing is adding 2 each time. That's what I'm doing. And because it follows a pattern, we can actually predict the terms. So if we're given 2, 4, 6, 8, and I asked you to tell me what the next term would be, or the next few terms, you could probably tell me that the next few terms would be a 10, 12, 14, 16, and you could continue to apply that same rule of all I'm doing is adding another 2 because I can see that's the pattern, that's the rule that my sequence is following. So that's really interesting as well. And so to apply that in a bit more of a complex sense, all it comes down to is substitution into formulas, and some of which are on your formula sheet. So again, I just really want to emphasize to be super familiar with your formula sheet. So that you know what formulas you need to know, what formulas you don't need to know, and which formulas you need to know how to use. So again, go look up your formula sheet. Super helpful. A bit of sequence terminology. When we're talking about a term in a sequence, that's denoted Tn. So for example, T1, when n is equal to 1, T1, that's the first term in our sequence. If I was talking about T17, we're talking about the 17th term in the sequence. So, and each term, I covered that one. This is what I wanted to say here, and n always has to be a whole number. So if I said let n equal 1.5, so I can talk about term 1.5, we can't have that. It kind of just messes with the pattern, and we don't really do it that way when we're talking about sequences. So n always needs to be a whole number, and this is the example of the sequence I gave earlier. So this, all we've got to do is count along: term 1, term 2, term 3, term 4. Term 4 is 8. Super simple. This here, I missed that out there. But what I wanted to say there is that T1 is also known as A. So that's our starting point. So we can define that. Or sometimes it might be T0, but that's a little bit more depth than we'll be going into today. So A is another kind of way that we talk about our starting point. And our last little thing I'll draw your attention to is if we have like an ellipsis, like a ... that's just implying that the sequence goes on indefinitely. So another thing to keep in mind is that if your common difference is positive, or if your common ratio is greater than 1, the numbers in the sequence will get larger each time. And the bigger the common difference, or the bigger the common ratio, the faster the growth. So it's an interesting thing. It's linear growth if you're talking about a common difference, but it's actually exponential growth if we're talking about a common ratio. So that's an interesting aside as well. And if D is negative, we're going to have linear decay. Or if R is less than 1, we're going to have exponential decay. So again, I just want to plant those thoughts in your mind to start you having a think about what that might mean. And we're going to revisit that in a minute. So sequences. Do you reckon, is this an arithmetic or a geometric sequence? What about this one? Arithmetic or geometric? So hopefully you might have been able to figure out that this is actually a geometric sequence, and this one is our arithmetic sequence. And how you can kind of figure that out is because here we can see that we're adding the exact same number every single time. We're adding the exact same common difference to get to our next term. we're adding the same common difference to get to our next term, same common difference to get to our next term, same common difference to get to the next term, and you get the picture. We could go on forever, and it's going to follow this linear pattern. So here, to link with the previous slide, because we have a positive common difference, we're seeing that linear growth because it's following that straight line linear growth. But here is where we have an example of a geometric sequence that's been graphed. Because you can see we've got term 1, and then it gets a bit bigger, gets a bit bigger, and then each time it's getting bigger and bigger and bigger because we're multiplying it by the same common ratio every time. And then when you multiply it by the same number again, and then multiply it by the same number again, it's going to follow this pattern. It's going to get bigger and bigger and bigger and bigger and bigger. So when we're graphing it, our line gets steeper and steeper and steeper, which is why we said before, this is our geometric sequence model, that exponential growth. And by exponential, like we're saying, it follows that exponential curve. So because here we have a positive R value, a positive common ratio, we are seeing that exponential growth. So that's a really interesting thing there. And to make a link, you might not be quite up to here in Unit 4 yet, but to link it to financial maths, which one of these would model simple interest and which one of these would model compound interest? It's interesting. Keep in mind that in simple interest, we're adding the exact same amount of interest every time, but in compound interest, we're multiplying by a common ratio each time. So that's an interesting link between how you can model a compound and simple interest using arithmetic and geometric sequences. So graphing, I already showed you a few graphs just before. Let me show you another one here. What else? Actually, I'll just quickly come back to this one. Let's show this one. If I pull up my laser pointer, you can see here that we've graphed n down the bottom and we've graphed Tn on the y-axis. And that is because we always graph n down the bottom. Sorry, let me skip forward again. And that is because Tn, so like the output, the number like that we're resulting in, depends on the term number. So term 1, term 2, term 3. So that's why we always graph n on the x-axis, and we always graph Tn on the y-axis. It's kind of, again, it's like explanatory variable and response variable to kind of make that connection there. So here, what kind of sequence is this? Hopefully you've been able to identify that that's a geometric sequence because we're multiplying by a common ratio. And here we have an arithmetic sequence because we're adding the same common difference every time. So you can see here that, again, we're jumping up by 2 every time. We're following that consistent pattern. Whereas here, we're multiplying by 2 every time. And I've actually already graphed, I've color-coded it in blue. We can see that in our geometric sequence, we do get that exponential growth curve. Whereas if you follow the red dots that are going to be popping up on the screen, you can see that when we graph an arithmetic sequence, like that line there, we actually get that straight line, that linear growth or decay if it's negative. And that pattern is actually, that separation is only going to get further as we continue further on in our trend, because this is going to keep following that same straight line forever, but this is going to keep doubling and doubling and doubling and doubling and doubling and doubling. So it's so interesting to think about how they're modeled and represented differently, and it's especially obvious when we compare them on the same graph. So like I said, geometric sequences, we're thinking exponential curve, whereas our arithmetic sequences are linear. Another important thing, you can actually generate a sequence using your calculator, and that's again using recursion. So that's really important if you want to quickly answer a multiple choice question or if you want to check your work. So to make your calculator generate a sequence, you take your calculator, you enter your first term. So with our 2, 4, 6, 8, 10 example, our first term would be T1. So our first term would be 2. So you'd enter the number 2 in your calculator and then press equals and then enter your rule. So which would, in our case, would be +2. and then I would press equals, which would give me 4, which is term number 2. I'd press equals again, and it would give me term number 3, which is 6. I'd press equals again, and it would give me term number 4, which is 8. So you can see my calculator, by entering the number and doing nothing, pressing equals, and then applying the rule, your calculator will realize that it wants you to generate a sequence, so it will follow in that pattern. So that's really interesting there. Okay.